In this introduction to vectors in the context of kinematics, we will remind ourselves of some basic vector properties and then introduce the very useful unit vectors, I hat, j hat, and k hat, who will quickly become our friends. And then move on to some vector arithmetic, specifically multiplying a vector by a scalar and then adding vectors using these two graphical methods, the head-to-tail method and the parallelogram method. So, 1. Basic vector properties. What is a vector? It's some quantity represented by two or more numbers, often drawn as an arrow to contrast it with a scalar, which is a quantity represented by just one number. So a vector is a quantity that has components, multiple numbers. That's why there are no vectors in 1D. So in 3D, a vector, A, indicated with this harpoon symbol over the top of it, has these three components, ax, ay, and az. The components themselves are scalars in blue. The vector itself, the collection of the three components, is here in red. So visually, here's a vector in red represented by that arrow. The components, like the legs of this right triangle, are scalars. And also the magnitude of our vector, that would be the length of this arrow here, is also a scalar. So if we put these absolute value signs around our vector, it becomes just a scalar. So I've got it in blue as opposed to red for the actual vector itself. In 3D, the generalization of that Pythagorean theorem looks like this. Ax squared plus ay squared plus az squared, if there's a z component square rooted, that gives us the magnitude. And again, that's a scalar. It's just a single number that we get by putting together these other three single numbers. So only the collection of the numbers is the vector with the harpoon over it. Okay, examples of vectors would include all of those things. Examples of scalars would include all of these things. And in print, you can identify a vector because it's usually bolded. So these, this typography here all indicates vectors, and a value in italics that's not bolded is generally recognized as a scalar. And once more, the magnitude of a vector being the hypotenuse, the length of the hypotenuse, that's always a positive value based on this definition here. Okay, so let's introduce our unit vectors. I hat, j hat, and k hat. Instead of a harpoon over the top of them, we have this little caret symbol, which is an alternative way of indicating a vector, a very special vector. These three vectors all have magnitude 1. They're called unit vectors, unit as in unity, as in 1. So they're vectors with magnitude 1, and that little caret we call a hat, so I hat, j hat, and k hat. Here's the definitions of them. I hat is a unit vector, a vector of length 1, of magnitude 1. Note I've got the vector in red, and the magnitude here, a scalar, in blue. Once we put those absolute value signs around it, it becomes a scalar. So from our expanded Pythagorean theorem, 1 squared plus 0 squared plus 0 squared square rooted gives us 1. It has magnitude 1. It points in the x direction. J hat points in the y direction. It also has magnitude 1. And k hat points in the z direction. That would be out of the page. It has magnitude 1. So they're like these three little sort of signposts indicating our three directions, x, y, and z. So to remember them, I recommend that as soon as you are 18, have them tattooed on your fingers here. So I've got on my middle finger, I hat pointing in the x direction. This has to be your left hand. Get out your left hand here. I hat pointing in the x direction. J hat, index finger, pointing in the y direction. And then K hat on the tip of my thumb here, pointing out of the page in the z direction. I hat, J hat, and K hat for our x, y, and z directions, or little unit vectors. One remark that a unit vector is as a dimensionless thing. The components and magnitude are just dimensionless scalars. So these don't represent lengths or times or amounts of force. the components are just dimensionless numbers. All right, let's put them to work here. Talk vector arithmetic, how we multiply a vector by a scalar. And so we'll see the use that we can get out of these unit vectors. Okay, so let's define some vector A as 3, which is just a number, so 3 is a scalar, times the unit vector I hat. So 3 I hat will become our definition of A. So that'll be 3, and then here is I hat, this collection of 3 numbers. I hat's X component, Y component, and Z component. To multiply this vector, I hat, by this scalar, 3, we just multiply 3 times each of the components. So 3 times 1, 3 times 0, and 3 times 0 to get this. These then become the components of the vector A. This is a x, a y, and a z, the 3, 0, 0. Visually, we took I hat, the little unit vector pointing to the right, and by multiplying that vector by a scalar 3, what we did was increase the length of I hat. We sort of scaled up the vector. Note that A still points in the same direction as I hat. So multiplying by a scalar doesn't change the direction, it just changes the length of your vector. So we see here that we can kind of construct A by taking our unit vector, the basic Lego block of a vector, and just scaling it up. Make I hat bigger, and we get the new vector A. Another example here, this one's familiar. You'll recognize Newton's second law here. Acceleration equals net force over mass. Acceleration is a vector, net force is a vector, but mass is a scalar, and so 1 over mass is also a scalar. So in Newton's second law, what we're doing is taking this vector, the net force, and multiplying it by this scalar, 1 over the mass. So we take our force vector and then rescale it by this factor to get our acceleration vector. So they both point in the same direction. Net force and acceleration will always be parallel, but they'll be of different magnitudes because of this scale factor here, the 1 over mass scalar that is being multiplied. They'll also have different dimensions because your scalar here has dimensions, 1 over kilograms. Another example, suppose we define a vector B as -2 times j hat. So -2 in blue, everything in blue is a scalar, times the unit vector j hat in red. Okay, so that's -2 times, here's j hat, this collection of 3 numbers, 0, 1, 0. We just take -2 times 0, -2 times 1, -2 times 0 to get these 3 components of B. So there's Bx, By, and Bz. So if this was j hat here, pointing 1 unit in the y direction, then B points like this. Note that it is in the opposite direction from j. That's what a negative scalar does to your vector. Multiply a vector by a negative scalar and it flips the direction of it and rescales it. So the 2 may be longer than j, but the negative flipped the direction. Okay, let's pause there.